Hi, we introduce here our FORESTRY timber workflows paper, where we present a speculative research on the potential of a linkage between the data practice and forestry and building sector. The background of this research lies within the search and interest in timber, where engineered timber provides a base for new structural and architectural opportunities. In this new material paradigm, timber takes over on completely new roles, besides the classic structural and architectural ones. It now has to compensate the negative carbon footprints of other building materials. In Scandinavia, the region where we live, the forest sector answers this increasing demand with large investments and is prepared to cover a substantial part of the building market of the future. However, timber has to be harvested in a sustainable way, and forests have, besides an architectural, many other important roles to play. To find a balance between the demands of use and habitat is an ongoing struggle, and besides the building industry, many other sectors see raw materials from the forest as a means for the transition to a bio-based economy. Recent research suggests that we are already harvesting too much timber and that the forests are no longer able to store the amounts of CO2 which our climate models assume. We find as well that our current timber practice in building industry are extremely wasteful, where less than 20% of the initial material from a tree ends up as a carbon sink in a building. The rest is considered waste. In our speculative project, we ask therefore how more of the raw material of a tree can be used in building components, where the data from the felled trees can help us to introduce a finer grading of timber, matching a more specific understanding of the performance requirements in a timber building element, and where the information provided from forestry sector on qualities found in timber can inform design and simulation models in building industries. The demand side, the building industry, bases its operation on the digital chain, where data from an early design proposition is in a set of interlinked data models further refined until production and operation. The forestry sector has developed similar data flows. Here, data is collected on forests and specific trees. This data is collected via satellite or ground-based operations. It informs selected harvesting. Sawmills use computer vision and CT scanning in order to obtain a precise understanding of the material qualities of each log, determine the cutting patterns, and follow each piece of timber from the log yard to the cutted and sorted board. Currently, however, all this data flow stops at the sawmill with a graded, standardized piece of lumber as a final product. In our project, we ask how this rich data from the forest could be linked with a final building product, a building element in an architectural structure. Our journey begins in the log yard of the sawmill. Here, CT scanners of our collaborator Microtech create image sets of each log within seconds. These two-dimensional image decks can be recombined into three-dimensional models. We've developed computational tools to read and analyze these models in order to obtain specific knowledge about the inner structure of a log, and integrate these volumetric models into our architectural modeling environment as Rhino Grasshopper. Here we can intersect the data with our design ambitions. For this project, we use a very simplified understanding of required wood qualities for our architectural design. High quality in areas of joints and structurally demanding areas, and low quality in other areas as a mid area of beams. We combine the different performance requirements from structural, fabrication, and tectonic level into a combined mapping. Similarly, we map out the qualities found in every timber log and match finally these two sets of requirements. The paper explains and evaluates in more detail which computational methods we use for this process. The T-scan data is furthermore directing our fabrication strategy. Here we derive from the T-scans more abstract vector representations of the boards, which specify the cutting of the CNC milling machines. This helps us as well to verify and position each of the uniquely and non-rectangular boards for fabrication. We evaluate our method with 2 physical prototypes. This allows us to assess the success of our method on a technological and sustainability-oriented level, but as well on an aesthetic one. Here we find that the contrast of the highly processed and the raw material provides exciting new surface expressions. We find that our methods allows us to use 140% more material from the initial lot than with a traditional approach. This growth in yield is based on more efficient cutting, but especially in a larger range of qualities, which can be used in our rolling structures. It's a large portion of wood is however wasted before the board reaches us. We are collaborating with players in the forest industry to create an even deeper connection between data from the forest and building design. Thank you very much. Good fun reading our paper.